And our next speaker is Sabine, and is going to be talking about computer-aided proofs for multi-party computation with active.
For the introduction. So this is joint work with Helene Hay, Alexander Karpyshev, Spitters, and Per Oechsner. We had a full morning now of MPC protocols now, so we're going back to formal verification now. So what is the goal of this work? We were studying formal security proofs of MPC protocols. There is something out of the literature on that, but not too much. So there's a work by Manuel and other people that considered Yao scaffold circuits and showed passive security in EasyCrypt. Then there's also a work by Butler et al. Who used Isabel cryptol. That is also passively secure. And in this work, we consider for the first time multi-party computation with active security. We're also doing that in EasyCrypt. So what we do here is we provide a full formalization and verification of an MPC protocol that is on the protocol specification level. Think of it as the pen and paper proof. So we implemented a protocol that is, we took the description from the paper, then we formalized the security notion. I'm going to talk about what these things mean later. And then the most interesting part is proving that the protocol actually satisfies the security notion. So what is the security notion? First of all, let's fix the adversarial model. I mean, for the crypto people here, this is clear, but we're talking about insider corruption when we think about MPC. So there are two kinds that we can consider. We can consider passive corruptions, where corrupt parties still follow the protocol specification, but they're still trying to learn more than they're supposed to learn. And then there's a stronger version of active corruption, where corrupt parties can behave arbitrarily. So we make no assumptions on how they behave. They can just ignore the protocol specifications, send malformed messages, send messages out of place, you name it. So the security notion that we consider here is in the real ideal world paradigm or simulation-based security, but we're not considering UC security here. This is just standalone security. So we're comparing a real protocol execution with a real adversary on the left side, with an ideal execution with an ideal adversary, which is this S here. And the ideal execution is going to be secure by definition. So in the real one, we have honest parties communicate with corrupt parties. In some sense, how the protocol specifies, except that the adversary can deviate from the protocol specification. And in the ideal world, we have instead a trusted party, F, that is going to compute the functionality for us. So the honest parties and also the adversary are just going to input their inputs and learn the result. And now the intuition is that if those two are indistinguishable, that is, if the output distributions are indistinguishable, then any attack on the real protocol is also an attack on the ideal model, which is assumed to be secure by definition. So to make this possible, the simulator, this ideal adversary, gets black box access to a real adversary and has to kind of interact with them. Okay. The next question is, what MPC protocol should we consider? We chose this one because it is so simple. It is the simple MPC protocols, how some people call it, by Maurer from SCN 2002. It's an information theoretic MPC protocol for arithmetic circuits over the ring ZP. So P doesn't need to be a prime. Arithmetic circuits means that we have addition and multiplication gates. The protocol is perfectly secure against static active corruptions of less than n over 3 parties. The protocol assumes a synchronous communication model that means that we have assumptions on the scheduling of messages, and it doesn't use broadcast channels explicitly, but you assume that there's a secure authenticated channel between each pair of parties. So I said it's information theoretic. How does it work then? Just to give you an intuition for those who know about MPC, the protocol is based on verifiable secret sharing. You start from additive secret sharing, and then build replicated secret sharing. And now you have, so shares exist multiple times, and then you can run consistency checks to give you a verifiable secret sharing scheme. So you get this verification, this verifiability from more communication. And now to evaluate a circuit, you do it gate by gate, as you would expect. So for an input gate, the party secret shares the input. For an output gate, you reconstruct the secret sharing. Addition is a local operation, and for multiplication, you do some local computation and then secret share values and do more local computation. So in this work, we focus on secure function evaluation, but the results extend to reactive functionalities. Okay, we've heard a bit about EasyCrypt yesterday, but let me give a brief recap. EasyCrypt is a proof assistant for reasoning about probabilistic programs. That is, in cryptography, anything we usually consider is a probabilistic program. That is, the program can make random assignments. EasyCrypt itself was originally designed for cryptographic game-based proofs, so we're extending that a bit here. EasyCrypt works internally on different logics, probabilistic relational Hall logic, and so on. I'm not going to go into detail for that. And EasyCrypt provides also some kind of automation that helps you with solving low-level proof tasks. So for our modeling in EasyCrypt, the first step we did was, of course, take the protocol that was defined in the paper and implement it. So EasyCrypt has a built-in probabilistic while language that we just use to express the protocol from the paper. There's just one caveat here that EasyCrypt doesn't have an explicit or a built-in mechanism for message passing. So what we did instead, we used a module as a wrapper that acts as the honest party. So there's no explicit message passing here between honest parties. But that is not too far from the actual model because we have a synchronous communication model. The only explicit message passing is when you interact with the adversary. So you pass messages to the adversary, of course, and then get back some messages. So to reason about arbitrary adversarial code, we use EasyCrypt's module system. So EasyCrypt allows you to define arbitrary abstract modules. That is, you just given a specification of an interface, you can use that to define how to communicate with an adversary without specifying the code. And that way you can quantify over all possible implementations that follow this interface. Also conveniently, EasyCrypt gives you access to the internal state of this abstract module that corresponds to what we in crypto usually call the view of the adversary. So you cannot read this value, but you can reason about it. And then security statements are expressed in EasyCrypt's probabilistic relational Hall logic. Okay, so what we would like to do is the following. We want to do a security proof in the real ideal world paradigm, or a simulation-based security proof. That is, we want to compare a real execution to an ideal execution. So, well, the way you do it is you write down what this means abstractly, and then you plug in the protocol, you find a simulator, and then you prove that the output distributions are indistinguishable, right? In principle, you could do that in EasyCrypt. We chose to do it another way because what makes it a bit ugly is, but that is inherent in simulation-based proofs, is that you compare two protocols to programs that are structurally very different. So here we have the actual protocol. On the other hand, we have like parties interacting with this ideal functionality and also kind of a protocol execution running that gets a bit messy. So what we do instead is we were looking for an alternative strategy that makes this proof a bit easier, but spoiler, it only works for this kind of protocols that we consider here. So what we do is we use a well-known technique from PL. We use non-interference, and we use a property that we want to prove that inputs that lead to the same output, according to the ideal functionality, yield the same observable behavior. Or in crypto terms, you want to use that when parties use inputs that lead to the same output, then the view of the parties is the same in both executions. So now we can reason about two executions of the same program. So we don't have this problem that we have, or problem. Not so nice thing. They were reasoning about two programs that are very different. But so this is what in crypto would be called indistinguishability, and we know that this is not the same as simulation-based security. But I will show in a moment how you can make that, how you can still use it for part of the protocol, and and still get a simulation-based security notion. So the idea here is that we deviate from the traditional approach. In active security, you usually do not consider robustness and privacy of the protocol separately. But here, in this proof, we actually do it. That allows us to use non-interference as much as possible to reason about the privacy part. And then, as a next step, we relate this non-interference-based definition that we get to the simulation-based one. So what we need is, this definition is specifically tailored to the protocol that we consider. So we assume that the protocol can be split into 2 parts. So for secure function evaluation, you can split the protocols into 3 phases. You have an input phase where all parties provide inputs. That would be here in this protocol that they secret share their inputs. Then we have a computation phase where parties evaluate the circuit together. Those 2 together is what I'm going to call pi 1 for the rest of this talk. And then there's a phase, part pi 2, which considers the output phase, which is here which is here reconstruction. And the definitions assume that this output phase consists of 1 round of communication where each party sends a single message to the other parties. Okay, so what is the security notion that we get here? We prove that for any adversary, the following 3 properties are satisfied. The first property is robustness. That is, with respect to the input that the adversary chooses, the protocol computes the function to be computed correctly. That is, you need some notion of extraction here. You need to give an extractor that extracts the adversary's inputs. But you need that for simulation-based security as well, for the notion. The second property that we're considering is now the non-interference property. So we call it input independence, and the idea is that pi 1, this input and computation phase, is independent of the actual inputs, at least what the adversary sees of it, which allows us to compare 2 executions on different inputs. And then the third property is what we call output simulation. That is a property of the output phase, and it basically means that you can simulate the output phase given only the output of the computation and what the adversary has seen so far. But it doesn't depend on the honest party's inputs. So more formally, a bit more formally, what we prove is that the distribution of the honest party's last messages depends only on the output and the adversary's output shares. So this you also need to extract those output shares now. Or phrased differently, if you have the output and the output shares, then you can compute messages for the honest parties for this last round that are consistent with what happened so far, or with what the adversary has seen so far. And of course, it is important that you can efficiently sample from this distribution. Well, so in this protocol, we have replicated secret sharing, so you can actually see what the adversary. So from the honest parties shares, you can actually see what the adversary is supposed to know. And the only thing that the adversary can do is choose to ignore these shares and pretend that that it has random ones, but that is not our concern. Okay, so what we did is we formalized those 3 properties in EasyCrypt, and then also proved that our protocol satisfies, whether the protocol that we consider has these 3 properties. But this is not yet the standard simulation-based security definition. So we also provide a proof on paper. This is a pen and paper proof that if a protocol has these 3 properties in this special form, then there exists a simulator for it, following the standard security definition. Standard simulator. Yes, so this is an idea of how this pen and paper proof works. Think of it as this is a simulator that a lot of people would come up with if they were asked to find a simulator for this simple protocol. So you start by running the MPC protocol on just dummy inputs for the honest parties because you don't know their inputs. And then at some point, the adversary needs to be committed to some kind of input, so you can extract that. Then you can feed this input into, or these inputs into the ideal functionality to obtain the output. Then you can also extract the output shares. And then finally, you can compute, the protocol needs to allow you to compute consistent messages for the honest parties based on what happened so far, based on the output. Yes? Yes, so I skipped that here, but in addition to these three properties, you also need that there exists an extractor for the input, yes. And also for the output shares. You're right. Yes. So if you have these three properties and the two extractors, then I can show you that the simulator exists. So the first part of the simulator, that you can run Pi1, the first part of the protocol, on dummy inputs, follows from input independence, because an adversary cannot distinguish whether you use the real inputs or just dummy inputs or random inputs. Then once you've extracted the adversary's input and queried the ideal functionality to obtain the output, you know that this is the actual correct one by robustness. And then finally, in the last round, you can compute these consistent messages because we have output simulation. And you can efficiently sample from this distribution, so you can just compute consistently looking messages for the last round. Okay. I'm a bit too fast. Okay. Well, let me summarize. What I showed you here is that computer-aided security proofs for MPC protocols with active security are actually feasible. This is the first time we've seen a proof like that. We also learned on the way that PL can actually give you insights in how to make the security proof a bit easier, even though what we did here was kind of very specifically tailored to this kind of MPC protocol. I don't advocate using this definition for other kind of security proofs. That was just, that made our life easier. But still, it is an interesting insight that you can do this kind of things. For the future, there's still a lot of progress necessary to make formal proofs easier to find. For example, I think we need a better understanding of like the abstractions we do in security proofs. Think of it as when you do a pen and paper proof. We often think that some parts are trivial or simple and we just skip over them. But unless you make it very precise what that means, you cannot just do that in a proof assistant. Like formal proofs force you to be very precise about that. So we need to get a better understanding about that. And hopefully, if you have a better understanding for that, then we might also be able to get automation to either get over these steps or maybe even at some point be able to find proofs automatically, even though I think that is a very ambitious goal. The paper is on ePrint. There's also a link to the code, and I'm happy to take questions.
Do we have time for questions?
Yes. Ariel? Oh, sorry. Go.
So if I understand correctly, so there are no computational assumptions, no reductions here, right?
Nope.
Everything is perfect. What made you choose EasyCrypt? I mean, if everything is perfect, if you just do kind of this simulation, you can probably do other things like even Proverif or stuff like that, which are model checkers. Kind of EasyCrypt, I think, was kind of designed in order to do reductions, but what made it easy for you to do that?
So you're asking why we choose, why we didn't choose, for example, a symbolic model, a model checker. Well, so in a model checker, you still have this gap that you need a computational soundness theorem to guarantee that it actually is the notion you usually want. Even though that might be easier because it's an information theoretic protocol. We just wanted to see what happens, what proof assistants can do so far without having to deal with computational assumptions. I mean, one reason why we chose this particular protocol is also because it uses secret sharing that is based on additive secret sharing. So the math is super simple. There are no polynomials. You don't need to do like interpolation to reconstruct. It is super simple.
How generalizable are these techniques to other MPC protocols? Can you take sort of these properties and reuse them and sort of reuse your handwritten proofs? I'm trying to get a feel for here how much of this can be reused for other MPC protocols.
So in principle, if the MPC protocol follows the structure, the special structure of the protocol, then you should be able to reuse the definition, even though I'm not sure if that is kind of giving you any new insights. I don't think this is the way we should be doing all our proofs. This is just a way on the path to understand what we should actually be doing.
Special the one. So if you have like 7 parties and t equals to like 3t plus 1 parties, does it go through? Did you try to look into it? I mean, the protocol is essentially the same, right? That's one of the simplicity advantages.
So the proof, okay, so the formalization is for n parties and 1 corruption. That's the case we considered.
Okay.
It should extend to t larger than 1. And I mean, the protocol, I didn't mention that, but it actually works for other access structures as well.
Yeah.
So that should generalize, yes, but we didn't try it.
Okay.
That was not the focus of this work.
I have a question. A couple quick questions. One is with regards to Ron's question. So EasyCrypt has this random tactic for that you can use an isomorphism between distributions, and I'm assuming that you needed to use that, which
yes.
So I think that kind of cuts in the other direction from being able to do a symbolic proof. The other question, we had some correspondence last spring about trying to work directly with the simulation-based proof, and by email, you suggested that there would be some hard things in terms of matching up the random assignments if you had to do it. So there are kind of 2 issues. One is having to do symbolic evaluation to deal with the structurally dissimilar programs, but the other is maybe there's something that would be problematic, and do you think there would be anything problematic?
Well, when we looked at it, it looked like there might be a technical problem that is EasyCrypt specific. I'm not sure if you can get over it, but that was one of the reasons why we choose to use another security notion.
Any questions? Okay, let's thank our speaker again.